morning everybody. We were looking at how to analyze a non-normal system, and we wanted to, so we showed that thermoacoustic system is non-normal, and we show that there is transient growth, and we also that transient growth does play a role in getting the triggering oscillations or the subcritical transition to instability, and we were looking at how to characterize this transient growth. So we came up with this parameter called G, which is norm of the state vectors or at some time t divided by the norm at time t equal to 0, which we showed that this is equal to the norm of the evolution operator. Then we said we will maximize this for all initial conditions, and then we maximize it for all times, and then we get the maximum growth factor. So are there any questions?
Actually, I didn't need this concept of the norm of the vectors.
Okay, so we will redo this question, redo this issue. So let's start from the differential equation dk by dt. The chi is the state variables or the vector containing the state variables, and you have evolution operator dk by dt plus L chi is 0, and this is, if chi was just a number, then you can integrate it the way you integrate a number. For example, what did they use? So this is what you would do if you adjust one variable, that is if it was a scalar, but you can do the same with a matrix, and we saw what is the meaning of matrix exponential, how to calculate metric exponential, etc. yesterday. So now we say chi of t is e power minus Lt chi naught, and we need the norm of this e power minus Lt. Now see, we know that the norm of a vector, you know what is a norm. How do you define a norm? Yeah, so so let me get to that slide, 1 second. So if you had a vector, you square them all and then you get the norm. Now this scaling by k1, it is like if you it's just the right amount of scaling. For example, you can use if you have x, y, z, and in one direction you have centimeter, another place you have meter, then if you square and add, it won't be right. Everywhere you have to have meter, then only it will make physical sense. So it's something like that, some scaling to make physical sense. Now the question is, so this is okay when you have a vector, but what happens when you have a matrix? Now who said square them, add, and you get the norm? I mean, you said this definition was okay in the beginning, just before the class started, that square them all and you get the norm, and that was okay with you. So who told you that this is okay, or who came up with this definition of norm?
Vector definition.
So who defined it?
I don't have an idea.
Huh? Somebody, human being defined it, and we define things such that in maths we come up with things, and then we try to interpret real life situation with these things. For example, you say 1 into 5 is 5, so that means if you have 5 chocolates, you give one kid one chocolate, and then you have 5 kids, they all got 5 chocolate. So you set up this maths, and then you see if we can apply it to physical. Now you say minus 1 into 5 is minus 5. Now so this is an abstract concept, no one, I mean you can't just prove this, it is just a given thing. You can interpret it as you owe me 5 rupee, he owes me 5 rupee, like that 5 people owe me minus 1 rupee, so then I call each person owes me minus 1 rupee. 5 times that I have to get 5 rupee, I put minus 5. So you define something, it may be useful or useless, and maths people, you see, they do lots and lots of things, only a small fraction of it we use, so they also don't know, and what they are doing, see what we are doing is what they did 100 years or 200 years back, and what they are doing now we won't touch till 2200 or 2300, and that is the way it is. And physicists are one step ahead. What physicists do 50 or 70 years before, engineers are doing now. I mean, and mathematicians are way ahead, but most of the things mathematicians do will be useless, some will be useful, which the physicists will take. Engineers will wait till the physicists take the subject to some level, then they will take it and start making things. So that is the way it is. So the norm was defined that way, okay, and you could have defined norm in some other way, and there are other ways of defining norms. What are some other ways of defining norm actually? You can also define norms as the maximum value of the set or something, that is also possible. Huh? Sorry? A supreme norm. You can define it whichever way. So you define something which is useful. Just to give you an example, now you have two players. Yesterday we saw Suresh Raina playing. I saw it actually, for a long time I saw a cricket match in the night. And he replaced Yusuf Pathan. Apparently both have same averages. So what they wanted was, they were sure that a lot of wickets will fall, and at that time they wanted some guy to stay till the end. So that was the objective. So if you look at Suresh Raina's average or Yusuf Pathan's average, they are same, but standard deviation is very high for Yusuf Pathan. He will someday kill everybody and many other days get killed himself. Raina is kind of a steady guy. So the average itself as a norm alone did not help in making a decision. Under that circumstances, you need some guy who not only has a decent average, but standard deviation is also low, so that he will make the average always, okay. So that is the idea. Now if we did not care about this situation and we had no problem if the middle order batted well and the lower middle order came and all we had to do was hit, then we need a guy with a high standard deviation, because a guy with a low standard deviation, he may not attempt these things, okay. So you see, so why did the standard deviation matter? I mean, because the circumstances demanded it. So what you need, you have to figure out what it is and use it, and there are lots of norms available in maths, okay. So we are taking 2 norm for some reason, and you can imagine why also, because like square of something, so you can already see in advance you have p prime squared plus u prime squared, so that is our hidden agenda. We want to get something similar to that if at all possible, okay. So now the question comes, what is the norm of this exponential operator? So we again look at, let us say take the books of linear algebra, search through everything. Yes, there is a 2 norm for that also, which is defined as the principal singular value, and so it does not make sense because singular value is a abstract thing, principal singular value is some other abstract thing, and norm is another abstract thing. So we have to, of course mathematicians develop abstract things, it is our job to find the right abstract thing and put it in a physical thing. So now what we need is what we can see from the numerical simulations and all the stories that I told earlier, that you can have eigenvectors decaying, but some direction you can grow. So growth has to be measured in some energy norm, okay. So in which case here we say something like p prime squared plus u prime squared weighted, okay. So now that is like the 2 norm of the vector space. Now so if you take 2 norm on this side, you take 2 norm on the other side also. So now what we need is some machinery which will find those directions and its amplifications. So that is the idea, and it exists as singular value. Now if you understand the meaning, which I will go through again slowly, then you will know why we choose principal singular value, okay, as the or why we chose 2 norm, or why this 2 norm is appropriate, and so on. So this part you understood, I guess, that singular value decomposition.
I understood this procedure.
Okay, now there are lots of decomposition in matrix algebra. Can you come up with some names? There are a lot of decompositions in linear algebra. Huh? LU decomposition, QR decomposition, SVD, singular value decomposition, eigenvalue decomposition, there are lots of decomposition. We have to pick what is necessary, okay. So when you look at science, now I say this is what is the thing done. When you see how this was discovered, we tried a lot of things and this is what works, and the guys before me tried everything, and I am sure they would have tried 100 things, 99 failed, 1 worked, and then we picked up. That's my experience, and I was trying to, so to be honest, I was trying to look at this, and I was really bogged down by this problem how to find the maxima, and a friend of mine said that in fluid mechanics they use SVD to characterize, and then I was trying to understand the meaning of SVD and so on, because they can do whatever they want, but if you are able to interpret that in our circumstance, it looks good. So in reality this is not the line of thought that happened when this ideas came, it is all, but now everything is done, now everything is neatly presented, but that is not the way things are developed. For example, in a movie when it is shot, they do not shoot in the order of the scenes. Sometimes maybe the last scene will be the first time that is shot, in between scenes maybe the shot next, first scene may be shot last, but in the end you edit and put it. So that is the way finally it is presented, so that the person who hears it makes sense, but that is probably not the way the guy who made it came up with. Okay, so that is some of the difficulty here. So we have this decomposition where you take any matrix A, and I said you can have many decomposition. Here you say U sigma V transpose, U is a unitary matrix, sigma is a matrix with non-negative numbers on the diagonals and zeros off the diagonal, and V transpose is the transpose of V, and U and V are both unitary matrices. Okay, so now we do SVD of our evolution operator. So we have dk by dt plus L chi is 0, and chi is this state vectors eta and eta dots, and this is the analytical solution, except that e power minus Lt involves matrix exponential. So we do SVD of this evolution operator, because that is what we are concerned with. Vector we know how to do SVD, right, I mean to get the norm, because you have chi naught and chi, we know the norm, we want to get the norm of this. So we write chi t as U sigma V transpose. Okay, I mean we are doing, let us see what happens. And now the physical meaning of this is, since V transpose it is a unitary matrix, so V transpose chi naught is actually resolving the initial condition vector into orthonormal basis of input vectors. So just like you have a vector and you can write it as Ax plus I mean Ai plus Bj plus Ck, or you can write some capital A times Er plus capital B times E theta plus some other thing times E phi. So similarly we have this basis, we use this V transpose as a basis, and it is resolving the initial condition along those bases, and they are orthonormal. Okay, so that is the idea. And now U multiplied by sigma V transpose chi naught, this represents the output normal as a linear superposition of components along the orthonormal basis, but the thing is you are having another basis. So the original basis may be like this, but this could be rotated or something. Okay, so there is no guarantee that you will follow the same basis. Now to understand the physical meaning, so the the singular vector, there are several vectors in the matrix, so we will have to look at that. So easy way to look at it is we multiply e power minus Lt by V from the right side. Now why do I do this? You can do anything you want, whatever you do, if it returns some results then it is good, many things will not return the results. Now for example, when I was a kid I was always wondering, why do people bowl outside the off stump? If they want to strike the wicket, you should bowl straight, but later I understood that if you bowl outside the off stump, people will try to take a swing at it and then you will get a catch and you will be out, so that is the objective. So now if you bowl outside the off stump and the guy does not care, he will just like our walls of Indian cricket, Rahul Dravid, just lift the bat up and then you just wasted a delivery. Okay, so something like that. So you can do anything, whether it is useful then it is, oh yes, again wonderful, a brilliant idea and all that. So but often these things are, they just do it not without, and then things work and then you construct why it is done. Okay, to be very honest about it. So the evolution operator is e power minus Lt, and we, let us see it acts on the most sensitive input condition. So this will give sigma 1, which is the maximum possible gain, multiplied by U1. Now the e power Lt can not only act on V1 but can act on V2, V3, V4, V5, V10. Now why there are these columns? Because we are discretized, so the size of the system is now dependent on how many modes you have. So you will have that many directions. Okay, so you do not have infinite number of initial conditions, you have finite number of combinations determined by the dimension of the system. That is, if you take 10 Galerkin modes, you will have 10 times 2, 20 vectors will be there. Okay, so e power Lt acts on one of these things, and you will get the output u and v are, they are unitary. So sigma 1 will show the amplification. Okay, so to see it in this matrix form, so A, if it acts on V1, you will get U1. So V1 is the right or left here, right singular vector or left singular vector, just look at your notes, or right singular vector. So the evolution operator acts on the, or any operator acts on the right singular vector, you will get another basis function which is U1, which is multiplied by a number. Now if it is acting on some vector here, let us say, you will get another vector here, somewhere here, with some other number here. Okay, so you can do anything. We are interested in the maximum amplification. See, generally in instability we are worried about the damage, how much it can grow. So if you know the maximum damage, you know, okay, this is like a bound, anything that occurs will be below this. So here our attempt is to pick the maximum growth. Okay, so if you were if you replace this A with the evolution operator, that is e power Lt, here it is, I mean in our norm, this is a slide from Peter Schmidt, I mean our L was minus of this. Okay, so this operates on V1, you will get U1 and times the sigma, which is the norm of this. Okay, now so you have optimum initial condition, and this is wrong actually, it is a right singular vector, and this is you get it amplified and you get the output direction. Okay, is it clear? So principal singular value shows the maximum energy amplification, and the corresponding right singular vector shows the most sensitive initial condition. So now it is clear, I do not have to, yeah, you had a question.
If that A matrix is non-normal,
yeah,
then that means in a general case you cannot diagonalize.
Yeah, no, we can diagonalize in, but the thing is the energy is not, so you have several eigenvectors, you are asking why it evolves independently or something.
Yeah, but a non-normal matrix in a general case it cannot be diagonalized.
Any matrix can be diagonalized. If you do eigenvalue decomposition.
Yeah, but that is only if you have the
Eigenvalue decomposition, you can do eigenvalue decomposition for any matrix.
yes, but then you didn't have an eigenbasis for the vector space.
You can have eigenbasis, it won't be orthogonal. So the problem is that, so if you have several eigenvectors, then each of them evolves as, sorry, e power lambda 80 sigma I equal to 1 to n. So each e power lambda 1t evolves one way, e power lambda 2 evolves another way, e power lambda 3 evolves another way, and that doesn't, e power lambda 1t how it evolves doesn't depend on e power lambda 2t. But the problem is you can't take the energy of the modes and add up and you will not get the energy of the system. So that is the only problem.
But we can do this only, and when we do this we are basically representing that A matrix in terms of the eigenbasis.
Yeah.
But then for the non-normal matrix we need not have n linearly independent eigenvectors.
That's okay, you can
So
still,
the eigenvector.
no, eigenvectors are independent,
No, but they will be independent, but you need not.
but they will have a dot product, will not be 0.
Yeah, but you need not have n linearly independent eigenvectors.
I mean if they are repeating. Yeah, so here you, okay, if you do not repeat it is okay, but the problem is you can have modes, but the sum of the energy of the modes is not equal to the energy system, that is the only problem. So in that sense they are, so if you have energy of the modes, you add the, take the energy in mode 1 and energy in mode 2, energy in mode 3, you add them, that will not be the energy of the system. So there will be some interaction terms you have to account for to account for the balance. So that is the only that is the difficulty. So it's in some sense, because of this problem, this is useless, because the modes energy of the modes does not give the energy of the system. You have to account for the interaction terms. Okay, so but otherwise you can do this. So next, yeah.
This will give us a maximum amplification
Mm.
and maximum energy to the
And the
system
type of
can-
excitation. So if you have basis functions based on first mode, second mode, third mode and all that, you will know how much to excite in each of them. So you may not necessarily, to get the maximum amplification, you may have to excite a combination of modes.
Like, is it like what is the initial condition you are talking? Yeah. Initially, the disturbance that you are giving to the.
Yeah, so let's say we have several eigen modes, okay, like here, but this initial condition is let's say this is the projection of the initial condition on each of the eigen mode. So you can disturb the first eigen mode or the second eigen mode or third eigen mode or 100th eigen mode, or you can disturb a combination of all these eigen modes. So you put the energy distributed into different eigen modes, and optimal initial condition means optimal direction means in which manner you distribute the energy into. A certain distribution will give the optimal initial condition. So this is the eigenvector decomposition. You can do eigenvector decomposition, or you can do like a orthogonal basis, which is very convenient. That's why I used orthogonal basis. I used the natural modes of the duct, so that's convenient actually. Any other question? Repeated eigenvalues also you can construct solution.
You need not have, if the dimension of the space is n, we needn't have n independent eigenvectors. Then if we don't have n independent eigenvectors, then A cannot be diagonal.
Yeah, okay, that's excellent.
So in a process, we generally say it will follow high entropy path, and similarly, can we say something here like it is following some high? Is there
No thought. I have no idea. I mean, first you have to define a entropy based on this. I think people who do statistical mechanics, they construct theory for crystals and all that, phonon vibrations and all that. So you could in principle do that, but there's no such theory as of now. I have not done it. So we can use the concept of pseudo spectra for studying normal systems. So before that, what is spectra? Spectra is a set of all eigenvalues. And how do you get eigenvalue? If A is the operator and lambda is the eigenvalue, what is lambda? When you say A minus lambda is 0, or you can say A minus lambda I inverse goes like infinity or something like that. So Z is a epsilon pseudo eigenvalue of A if it satisfies Zi minus A inverse is greater than epsilon power minus 1, or we can say Zi minus A is like less than epsilon, one of these things. So that means you are not looking to satisfy the relation exactly, but we will put a small number and say okay, within this number you will satisfy the relationship. Or if you were looking at a resonance phenomena, your amplification goes like inverse of the distance between the forcing frequency and the resonance frequency, right? There is a 1 over a distance kind of relationship, and as you approach the resonance you get infinite amplification. But here instead of getting infinite amplification, we are looking at large amplification. So epsilon is 0 and then this becomes eigenvalue and this inverse gives the amplification. But instead you say epsilon is a small number, let us say epsilon inverse is 10 or 100 or 10,000, these values depend on the system itself, what is large and what is small. So you can actually have large amplifications even if you are far away from the eigenvalue for non-normal systems, and then we can take a look at that with the pseudo eigenvalue. So the way to compute is to have the set of all points on the complex plane whose minimum value of singular value of zi minus a is less than epsilon, but you need not worry about how to do the calculation, but let us look at the concept. So if you take an operator and look at the pseudo spectra, first you can look at the spectra, so you calculate the eigenvalues and these dots here are the eigenvalues. Now you say you do not satisfy this a minus zi is 0, we do not do that, but a minus zi is less than some epsilon, and you take this epsilon contours, and then you can actually calculate the contours for z, and those are these contours. So the eigenvalues themselves can be on the left half plane, let us say for the evolution operator, but the pseudo eigenvalues can spill to the right half plane. So there is another way to look at it. I first said you can think of exciting a system with a frequency, and as you come close to resonance you get large amplification, but if you are having pseudo resonance you may have large amplification away also. For example, whatever value you have here for epsilon you are getting here also, everywhere also. Now we think of, let us go back here, this operator A. Now we do not know A exactly, or let us say A is perturbed a little bit. We have an electrical heater in our experiment, and let us say the heater power changes slightly or something, so the evolution operator can change, or the velocity, mean velocity can change slightly or anything. So you do not know, or you do not have the exact A, but you have some A is perturbed, and you look for the eigenvalues of that perturbed matrix. That is another way of interpreting pseudo spectra. So the crux of the matter is, if this pseudo eigenvalue crosses to the right side, then there is a possibility of transient growth. So contour should protrude to the right half plane for the system to exhibit transient growth, and this is like a necessary condition for transient growth, and you can use this concept of pseudo spectra and we can get bounds on the transient growth and so on, but I would not go into too much detail. So if you look at the evolution of this e power lt for a non-normal system, you have a growth and decay, and the decay is determined by the eigenvalues, which is what is called spectral abscissa, and this peak is determined by how much the pseudo spectra protrudes to the other side, and this initial slope is determined by the numerical abscissa, because the eigenvalue of minus L plus L transpose over 2. This you must have studied in maths. I will derive it otherwise. Glasses, 1 second. So I am following Farrell here. So this is, I am using his notation just to, so that you can read the paper yourself. So this is like the inner product of the state vector with itself, and this is like at some time t divided by inner product at some time 0. So this is like the norm, 2 norm, square of the 2 norm, and this we can rewrite this as e power at u naught. We know that is a solution. Now we can use the definition of adjoint. So we have to look at e power a dagger plus a t. So this depends on this quantity. So you should strictly speak write I. So this is, what kind of matrix is this? This is a symmetric matrix. So we should be able to look at its eigenvalues and tell what is the whether it's growing or not. So this thing's eigenvalue actually a plus a transpose divided by 2, that's eigenvalue is called numerical abscissa, and that will determine how much is the initial growth, and then how far it grows determines on the pseudospectral axis, how much it protrudes to the other side, and the decay, asymptotic decay is determined by the eigenvalues or the spectral abscissa. Okay, that's written here. Okay. Yeah, so we saw this equation. What is this? This is our energy corollary in the presence of heat release given by Lord Rayleigh, and predicting transient growth using Rayleigh criteria requires the precise knowledge of initial conditions, and see, ambiguity of initial conditions due to noise, because you cannot precisely know the initial conditions, make the identification of transient growth using Rayleigh criteria very difficult. There is one more problem. You see this triangular brackets, so normally we try to average over a cycle to find out whether energy in this cycle is less or more than the energy in the next cycle. But when you have transients, we saw everything is changing, so we can't really identify, pinpoint a period, because there are many periods available. So what is the period itself is a question, so we can't really use this to make any study of transient growth. But you can look at the operator, everything we did, the G max or the pseudospectral abscissa and so on, they and the condition that the pseudospectra should protrude to the right side, etc. They just depend on the evolution operator, and they are actually giving the maximum possible growth. So we are not able to pinpoint and study for this initial condition this is the growth. For that, of course, you can do the evolution and get it, but this G max is like a upper bound, that's the maximum transient growth you can receive for any initial condition together. But that just doesn't depend on initial condition, because it's maximized over all initial condition, it just depends on the evolution operator. Okay, is this clear? So let's look at some experimental stuff to see if all this is really there or a fantasy. So this is you can see this is data taken from Louisville, it's a friend of mine, a colleague. Experimental investigation of limit cycle oscillation in unstable gas turbine combustor. This is a real turbulent combustor actually. You see a lot of noise here and then suddenly it takes off. So in reality it is not like a system is completely sitting silent and then bang on initial condition happens, and then so you have noise, and noise means all kind of possible states are there. So eventually you hit some right initial condition, because any initial condition is like we think, okay, this is some time t, this is the values, and then how we progress. So noise can act as like it does the same purpose as initial condition, and so and what he has written, although large amplitude disturbances are generally required to initiate unstable oscillations in non-linearly unstable systems, a systems may be non-linearly unstable at low amplitude disturbances that are the order of background noise level. This scenario is somewhat analogous to the hydrodynamic instability in a laminar Poiseuille flow. This book was published in 2005 before we came up with this theory of non-normality, but what he has written is he is talking about low amplitude disturbances. So generally triggering was perceived to be caused by high amplitude disturbances, but the people who did experiments noticed that you can see it at low amplitude disturbances. Now in hydrodynamic stability, this revolution happened in 90s, and I think 90s, late 80s perhaps it started, 90s the battles happened, in 2000 maybe the people won the battle. So there the non-linear terms are energy conserving, that means all the growth is because of linear mechanism, non-linear terms just redistribute the energy between the modes. But in thermoacoustics our terms are not linear or non-linear, they are not energy conserving, because you see it adds energy p prime q prime. So we do not have this situation, so we can actually get triggering without transient growth also by large amplitude excitation with only one mode analysis, but because of the interaction between the modes or the non-normality and the non-orthogonality of the eigenvectors, you can get transient growth starting from small amplitude disturbances, and then with the small amplitude disturbances can actually take the system to another state, limit cycle. So that is this somewhat, but I asked him, he said he did not know really why he wrote the word somewhat, but it sounds perfect now. I met him recently 2 months back and I asked him, did you really knew what happened? He said, I had no idea, I just wrote this and it turned out to be working. So I showed you this hysteresis. Now you see the same pattern, you can see this is experimental data from MATB 2003. This thesis can be downloaded from internet, very nice thesis, and it is, so you come here, you have to come to 1050 watts to go up and you have to go back to 650 watts to come down. So if I just draw a line in between, this is very similar to the bifurcation plot I drew. There were this this is the threshold amplitude over which you have to cross, so this is the unstable limit cycles are lying somewhere here, right, and this is the stable limit cycle, the green, okay. So what our theory, you can make any theory and all theories are wrong because you always make a lot of assumptions, but can you explain something? So is there any use to your theory? That is the idea, okay. So that means it has to match or it has to predict some things which are observed experimentally. So that was in a recade tube. We see it in a pre-mixed flame also. You push the flame and it becomes unstable in one way, but when you come back you come like this and the flame becomes unstable here at that particular location of the position of the burner. And to come back, you can't just come back right here and become stable, you have to go a little bit further to make it stable. So this is in a diffusion flame, this is a pre-mixed flame. So again you have to come here to go unstable, but you have to go back at another place to become stable. So hysteresis is the order of, I mean there is a lot of hysteresis to be seen in any kind of experiment. So 2 of them are our experiments, one is in the somebody else's experiment. Now this is the our experiment where unfortunately the audio is not playing. This is like a noisy system, the noise stays as it is, but some other time the noise suddenly goes to instability. In fact if you do the experiment running with at different levels of noise, for example this level of noise here, for example if you had certain level of noise, you do the experiment 100 times, 70 times it triggers, 30 times it doesn't. So now you talk about some kind of probability because noise is stochastic, so you can only talk about probability terms. I will not speak too much about this. Just want to show one last thing. So we construct our phase space, okay. You can use all the vectors, you can construct the phase space, or there are techniques with which you can construct reduced order model. So there is something called Taken's embedding theorem, and if you have time series data, from that you can construct the phase space and so on. I do not want to discuss any of this, but in this phase space this is our stable fixed point and this is my stable periodic solution, which is also called limit cycle. Now the issue is how we are going from which is the easiest way you can, or which is the smallest energy which will take you to the limit cycle. That's the question here, and this is from Matthew Juniper from Cambridge University, is my friend, done some follow up on our work. So every point in the state space is either attracted to the stable fixed point or the stable periodic solution, which is limit cycle. So although we say instability, the limit cycle is a stable solution actually, it's just that there are oscillations, we do not like it, so we say that is unstable, but in reality the limit cycle is a stable periodic solution, isn't it, the stable limit cycle. So some points go down here, some points go up here, okay. Now there is really a basin boundary which is which separates the two basins of attraction, and there is a basin boundary which separates this basins of attraction, okay. So a surface separates points that evolve to a stable fixed point from the points that evolve to a stable limit cycle. So there is this possibility, and there's actually, you can actually find an unstable periodic solution on this basin boundary. That means the solution, but you can't stay there because any slightest departure will take it out of it. So in principle there is a solution, but you can't have it there, it's not stable. So if you have any questions, please ask me. So we want to find the lowest energy point on this boundary, okay, that's the idea. So you have a boundary, and the question is whether the boundary is like a football, everything round, or is it distorted. From this picture you can imagine that I am hinting at a distorted. So let us say you have this limit cycle, and let us say this is the lowest energy point in the unstable periodic solution. Do you have to hit the system with at least that much energy, or can this dimple be dimpled such that you can even have lower energy and still go up to the limit cycle? That is the question. So we look at different topologies. This is a cartoon given by Juniper. There are different types of potatoes. So see, this is it doesn't have any grooves inside, but here already you can see there are some grooves where if the unstable limit cycle is lying on this topology, you could still be inside this pit and you can have lower energy. You can have this kind of potato also. The topologies can be quite complicated. So the optimum initial condition actually grows transiently towards an unstable limit cycle. So it first starts from some low energy point, goes to an unstable limit cycle, just loops around it for some time because it can't really stay there. Now unstable limit cycle will have several attractors which are attracting to the limit cycle, but there will be one neutral direction along the limit cycle and one will be kicking it away. So eventually it will try to float around here, but then suddenly it will just take off. It will have a slingshot and it will go towards the unstable limit cycle. So you can read about this by reading this article in Journal of Fluid Mechanics by Matthew Juniper, triggering in horizontal decay tube, non-normality and transient growth and bypass transition in Journal of Fluid Mechanics. Very nice paper, and they have used calculations using our decay tube model with that Haeckel's correlation and so on, and use the same solution and try to look at the nonlinear dynamics. You have any questions on that? Sorry?
Unstable, you would say. Can you explain what's the difference?
Yeah. So let us say this is amplitude and this is heater power. Not putting any units, but so let us say you come till here, you are increasing the heater power. At some point you get to instability. Okay, so these are stable fixed points. That means you can be here and I am coming this way, but the system is still staying there. Okay, here also there is a solution. In fact, in our decay tube, first let us look at what is stable versus what is unstable. So you can have the decay tube, just have the base flow, that is a solution to equations, right, isn't it? If there are no perturbation, your solution will be satisfied, trivially satisfied. If u prime, p prime, q prime, everything is 0, won't your equations be satisfied? It will be, but you can't have the solution here once the heater power is jacked up. So there are solutions, but I have put hollow circles. That means these are unstable fixed points and these are stable fixed points. Now I come here and I have solutions. That means even if I disturb the solution, it will come back to that. So if I say this is some kind of curve, this is the limit cycle, what it traces. So I push it to any of the points inside the envelope. So and you look at points starting from within this gray area, how they evolve. Eventually they will all, so after some time, converge to this. So that is like, it is a stable limit cycle, you can push it but it will come back. But let us have another scenario where I have another case. Now I have a point and I push it, instead of converging it is actually diverging away. So there is a solution that is possible, but it can't stay there, or only time it can stay is in principle at minus infinity or something, which I mean real time you cannot stay there. So there is a solution, it can be satisfied but you can't find it, so that is unstable solution, and you can't find it because it can't stay there, because any perturbation will be taking the system away from that. So in this case, for example, you can imagine there will be these unstable limit cycles somewhere here.
Suppose in the system I am just taking the gas and not the heater, heater power taken in the gas from by the gas is plotted here. So in that case, once it goes to unstable mode, it will take in more power now, because the amplitude vibrations here are high. So from heater, the power absorbed into the gas will be much more in the unstable mode than in the stable.
Yeah, so
like the heat,
you are talking about excessive heat transfer from the, so mean energy is taken more, yeah, that is right, because of streaming and so on.
So like is that the reason why this hysteresis comes? Because then you have to use lot more energy to take it back.
No, hysteresis just means that once you are here and you are going back, so I should stand this up. Once you are here and you are going this way, you are already outside the basin of attraction, so you can't find this point here, it will just instead stay here.
Like doesn't it have,
so you see, you have this unstable basin boundary separating these two solutions, and it depends on whether you are inside the boundary or outside the boundary. So if you are going this way, you are always inside the boundary, so you will fall back here, but if you are coming this way, you are already at such loud amplitude, so you can't go back here because you are already outside, so it is being attracted there.
and one more thing is, if we escape through the lower energy part of the basin, but there is a possibility that you don't need to reduce that much energy to get into the basin, you can enter through some other point.
Right. So it depends on the direction.
That will be will that affect the hysteresis of the system?
No, this is the this diagram only indicates the final state or the asymptotic state. It does not talk about what happens at the initial thing. So just it's a plot of solutions, but in this plot here of this phase space, yeah, you can actually, if you have a large energy but you are inside here, then you can fall back to the basin boundary. But if you are already on this limit cycle, right, and you change some parameters, so you will get a different limit cycle which will be very close to this limit cycle. So just slide to that rather than come in.
Because what I am asking is, when we write this amplitude versus heater power, shouldn't we take the heater power taken by the gas rather than the heater power we are giving?
Yeah, that is okay. See, we are unable to measure it, so in this case, in the theoretical calculation, that is they are the same. But the experimental people, they cannot measure the heat amount of heat taken by the gas, so they will put.
Is that the same in theoretical and experimental? Because
see, in experimental you can only measure the current and voltage and all those things, the electrical power. If there is a way to measure the power taken by the gas, so there will be some losses, and in the cable some amount will be lost by radiation and all that. So if you can account for all that and measure, yeah, it is possible. But in theory both are same. So in theory, in the correlation what we used is heat taken by the gas, but the experimentalists can't quite measure it. I mean, it's in principle possible, but very expensive, you need to use some laser induced fluorescence or something. I mean I won't even dream of doing those things. So it's much simpler to plot input power. So in a dynamical systems you can plot anything you want as the bifurcation parameter as long as it affects the system. That is the good thing about that machinery. Any other question? Okay, so we will stop here.